YouTube, welcome back. Today we have a new approach, a new solution for problem number 55 jump game. The previous solution we get time exceeded due to that we are looping a lot and we have time complexity of 2 in power of n, and this wasn't good for all the solutions. For all the test cases for this specific problem, and today we will try to optimize this solution. Let's first try to read the problem again. So if there is someone who didn't watch the previous video, he will not feel like he is left out. So problem number 55, jump game. You are given an integer array called nums. You are initially positioned at the array's first index, and each element in the array represents your maximum jump length at that position. Return true if you can reach the last index, or false otherwise. Okay. Example, we have example 1. We have like input nums. It's true because we can reach to the end by going from the first one. We can jump 1 step, and from there we can jump 3 steps directly. In this one, false, because no matter what value we take, we end up in the 0 in this position. So if we try to jump 3 directly, we'll end up in here. If we jump 1, we have 2, so we have 2 ways to jump, 1 directly and we end at 0, or 2 directly, we'll end in 0. And if we jump 2, from 3 we jump 2 instead of 3, we'll have on 1 and we end also in 0. So there is no way that we can reach the end index. And in the previous video we come up with this solution. However, we found the solution didn't work with all the other solutions, all the old test cases, because we have time exceed because we were trying every index. So there is a way to improve this one by using a dynamic programming top to down. So basically, top-down dynamic programming can be thought of as optimized version of the backtracking that we are currently have right now. It relies on observation that once we determine that a certain index is good or bad, good that we can, if index is good, that we can reach the end from it, bad we can't. And this result will never change, and this means that we can store the results and not need to recomplete it every time. So basically we will use memoization with the recursive function. So let's just start from the beginning. I will create an index object, and this one will use to track to know what is the good, which will be 0, and we have bad, which will be 1, and we will have unknown, which will be 2. And I will create a memo array, so we memorize every value that we are in, so we don't have to go through all the values again. So it will be new array. It will be from nums dot length, and it will be dot fill. All of them, it will be index dot unknown. Okay, and I will create the function, which will be the recursive function, which will be const can jump from position, and it will be a function that takes an argument, and it will be a position argument, and I will call this function. I'll return this function, return can jump from position, and I will add 0 to it because we're starting from the 0 1. And before I do anything, I will do something, and let's just try. We'll discuss it furthermore, but just keep it like that. I will say if memo dot nums dot length, if we have it in the memo, -1. If we have the last it will be equals index.good, index.good. And we talk about why we do this later, but we have to finish this one so this line will be understandable. So let's just start in the function here. I will say, okay, first we're creating a recursive function with the memoization right now. So we're using a dynamic programming solution here. So it's important to know that when we are using a memoization or a recursive function, we should find the base case because we don't want our recursive function to run endlessly. So we have if, I'll create a base case if memo first, if memo of the position, if memo of position doesn't equal index of unknown. If that position doesn't equals index of unknown, that means because if you can see here in this array, we stored all of the indexes for the array, and we give them the unknown values. If the index doesn't equal unknown, that means we did visit this index before. So what I will do, I will return memo of that. I will return true or false, but however, I will see memo of that position equals index of good. If that was the case, I will return true. Otherwise, I will return false. Okay. And I will have const. I will have the farthest jump, and this variable we use to calculate farthest jump, and in this value we used to calculate the farthest jump that we can jump. So basically we have a math.min position plus nums of the position, and we will have nums dot length -1. Length -1. So basically here we make sure that we don't have a value that bigger than nums dot length. So we are within the length of the element of the array. Sorry. So I'll create a for loop for let next position equals position plus 1. At the same time, the position should be less than or equals the farthest jump, and also the next position will be plus plus. Okay. And I will make if statement if can jump from position, because we call this again, it's a recursive function. And right now I will try to call this function on its nexts to know if we can jump it or not. If we can jump next position, if we can jump from this next position, we add it to the memo of position, and it will equals index of good. And sorry, it's not a big I, it's small I. and we return true. If we didn't return anything, we have memo of position equals to index dot bad, because that means that we couldn't get to the end, and we return false. Okay, let's try to first, let's run it. Let's see if it will work or not. Okay, it didn't work. Why it didn't work? Let's see. Expected false, and we return true. Why we return true? Let me see here. First of all, I have unknown is 2, right? And good is 0, bad is 1, and I feel it was unknown. I'm calling this function. Okay, if memo.position doesn't equals index that unknown, I will see return memo of position. I want to know if this equals index of good, I will return true, otherwise I will return false. After that, I will have the farthest jump, which will be math.min position nums of position and nums.length -1. And after that, I will do for let next position equals position +1, and next position, next position. Let me run this one right now. Yeah, it worked. Let's try to describe here. And after that, let's run it. So basically, the code here defines an index object to represent 3 possible states for each position in the array: good, bad, and unknown. Indicates that it's possible to reach the end from the position. Good indicates that we can reach we can reach the end from that position. Bad indicates that it's not possible, and unknown is used to as an initial state. Okay, the memo array is used to store the computed state of each position, and it's initialized with index.unknown for all positions. After that, the can jump position, this one, let me just the can jump position, the can jump from position function is similar to the previous version that we created in the previous video. It checks if it's possible to reach the end from a given position and memoizes the results. Before performing the recursive check, before performing the recursive check, let's just put this one here. Before performing the recursive check, it first checks if the memoized result is available. If it's available, it returns true for index.good or false for index.bad, and continues with the calculation for index.unknown. The rest of the code follows the same logic at the previous video. Basically here in this one, we check right now. We try to run the can jump position in the next position, and we check them all. Here also in this line, if you don't know why we do this one, for this one, if we can't find any position, that means we can reach the end, so we return the position.bad, and we return false. And here in the memo, I want to make sure that the end is good, because when I reach the end, if I'm reaching the end, that means we are in the end right now, so we return true because the end is good. Because if you are in the end, you can go to the end, you're already in the end. So the can jump function initializes the memo array and sets the state of the last position to index.good, since it's always possible to reach the end from the end. Finally, we call the can jump from position to start the process with the initial position and return the overall results. Let's submit and see if it will work or not, but I guess also we get limited exceeded. Okay, we didn't get limit exceeded. We have a good one. We have an awful amount of milliseconds. We're beating 5%. We have a next solution also. It will not be better. I guess it will be the same. And after that, we have the lost solution. Maybe we have 2 more videos. The last one will be, we will use a greedy algorithm. It will be way more better than all of that. But it's important also to discuss the programming, the dynamic programming solutions, because it's a big part of any problem interview that you will see. So that's it for this video, and I hope you like my content. If you like my content, make sure to subscribe and hit the notification bell so you never miss a video, and see you guys in future problems.